Okay, so now we have hopefully established a decent foundation for understanding thermochemistry. Now we're going to take a look at how we can tie that into now making some of these measurements, for example, in the laboratory. And the process of measuring heat changes is called calorimetry. So the word calorimetry is just a combination of, losing my space here. It's a combination of calories and then metering, or so metering here means measuring, right? And then calories is heat. So measuring heat energy, heat changes, that process is done in a device called a calorimeter. That's how you pronounce that word as well. And we will actually do, if you haven't done it already, we will do an experiment where we make a calorimeter, a very simple one, in order to measure these heat changes and to do all sorts of calculations. Now, when it comes to doing calorimetry and using calorimeters, we need to know a couple things. The first thing is called the specific heat or the specific heat capacity of a substance. I'm going to write that out because your book uses a term to describe what this is. If you look other places online or another textbook, this term is also referred to by a slightly different term. Sometimes it's called the specific heat capacity. And the abbreviation sometimes is a little different. Sometimes it's a lowercase c, or your book uses lowercase s. Either way, it's defined as the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius, right? So it's specific because now it's specifically raising the temperature of 1 gram by 1 degree. So what it's telling you is, it's giving you an idea of how much energy do you need to provide to increase the temperature of this thing, of 1 gram of this thing, by 1 degree Celsius, right? So it's giving you a really good way to compare specific heats of different substances. I'll give you an example of two things that we'll see on this chart, table 10.2. So if we look at the specific heat capacity of, let's say, like a metal, okay, so let's look at copper, Cu. Okay, a specific heat capacity of 0.385. So the units here will be 0.385. The units are joules per gram degree Celsius. So it takes, in other words, 0.385 joules of energy to raise the temperature of 1 gram of copper by 1 degree Celsius. And if you compare that to a very common substance like liquid water, you would see that the specific heat of liquid water is, in comparison, extremely high. It's 4.184 joules required to raise the temperature of 1 gram of water by 1 degree Celsius. So it is much higher for water than for copper. And if you think about this, right, based on your experiences with water and metals, uh, and you probably know this from experience, right? Metals heat up and also cool down quicker than than water, and it heats up and cools down to a much greater degree or extent than water does, and that is a direct reflection of the differences in specific heat. Something with a small specific heat or a low specific heat will heat up and cool down a lot quicker than something with a much higher specific heat. So the specific heat of water is about over 10 times higher than the specific heat of copper. So for example, when you cook, if you have your pots and pans on at home, they are typically metals because metals absorb that heat from the stove very quickly, and they also release the heat to the thing inside the pot of the pan very easily as well, right? But water, it takes a lot more energy to increase the temperature of water by this to the same extent, and that's actually a good thing if you think about it. The majority of the surface of the planet is covered in water, and every time the sun comes up, the water doesn't boil away, right? And that's because of the high specific heat of H2O. It takes a lot of heat energy to raise the temperature of water. and it takes a much smaller amount of heat energy to raise the temperature of an equivalent amount of a metal by the same amount. So that is the specific heat capacity of a substance. The heat capacity, which is abbreviated as an uppercase C, this is an upper or capital C, is the amount of heat needed to raise the temperature of an object. So just something in general, by 1 degree Celsius. All right. So, as we saw, the specific heat capacity, units of joule per gram degree Celsius. Heat capacity is just in units of joules per degree Celsius. It's not per gram. It's just in joules per Celsius. So, for example, if we look at the heat capacity of water, right? If we take the specific heat capacity of water, if we need it for a kilogram, we just multiply it by the amount of substance that we have. Right? So the object can actually just be a given quantity, a particular substance. So there is an equation that we can use, and this is what we're trying to get to, that we can use to calculate the heat changes or the heat associated with temperature changes. And this is where this is going to be very, very useful for us. We can calculate heat changes by looking at temperature changes. And the equation is often called the heat equation. It's often written as Q, heat, is equal to M, the mass, times C, the specific heat, times delta T. Okay, your book uses the same layout, but slightly different abbreviation. It uses M times S, S for the specific heat. Right? These are the same thing, times delta T. And that's using the specific heat. Or we can say Q is equal to the heat capacity C times delta T, right? If we have a given quantity of a substance, again, here we have the delta designation, right? So the change in temperature would be the final temperature minus the initial temperature, right? Final minus initial always whenever you see that delta. So let's take a look at a simple example. It says calculate the amount of heat required to heat 1.01 kilogram of water from 0.05 to 35.81 degrees Celsius, right? So once you see calculate the amount of heat and you're given masses and temperature changes, we're probably going to use the heat equation. So Q equals M times C times delta T. Okay, so my delta T, it's probably the first thing we can identify here is the final, is the 35.81 minus the initial 0.05. So that's going to give me 35.76 degrees C. The specific heat for water, okay, that is, so C, and again, you don't need to look up, I'm sorry, you don't need to calculate specific heats. I'm sorry, you don't need to memorize specific heats. You will either be provided with them, or you can look them up on tables, stuff like that. So the specific heat of water is 4.184 joules per gram degree Celsius, which means if I'm given the mass in kilograms, okay, that M there is 1.01 kg, I actually need to convert it to grams so I can use it. So I can use the specific heat value. So that's a metric conversion. Every 1 kilogram is 1,000 grams. So this is 1010 grams. So I have all my things I can use now to substitute into my equation, my mass, my specific heat, and my changing temperature. Okay, so I have Q. So the mass there is 1010 grams. Keep track of the units because it will help you figure out whether you've set this up correctly. 4.184 joules per gram degree Celsius. And then the temperature there, temperature change is 35.76. So degrees Celsius go away, grams go away, we end up with joules as the units. So we evaluate this to 3 sig figs, we get 151 kilojoules. Okay, so fairly simple equation, but you want to make sure that you do the other sub calculations involved before you actually get to the main calculation. So that may involve just calculating delta T. It may involve converting the mass to the correct unit. It may involve finding or locating the specific heat capacity. We need to do all of those in order to solve these types of questions efficiently.